Hey there, and welcome. Have you ever really thought about how a simple clap travels across a room, or how a quiet whisper can carry a secret? Today, we're going to dive deep into the invisible world of sound. We'll break down how every single sound is born, how it makes the journey to our ears, and even explore the amazing symphony of sounds that exist completely beyond our ability to hear. So, let's get right into it.
It's a great question, right? I mean, they sound totally different. A sharp clap, a soft whisper, a huge orchestra. But believe it or not, they all share one single fundamental starting point, and that is vibration. Yep, that simple little wiggle is the secret sauce behind every single sound you've ever heard. Ever.
All right, so here's our game plan for this explainer. We'll start with the birth of a sound, then we'll follow its path to see how it travels. After that, we'll dissect the anatomy of a sound wave itself. Then we'll connect all that physics to our own perception, discover what's happening when sound bounces back as an echo, and finally, we'll listen in on the secret world of sounds way beyond what humans can hear. Okay, let's kick things off with the origin story. And it's a simple one. Every sound in the universe, whether it's the tiny buzz of a bee or the massive boom from a concert speaker, it all begins with this one simple action. So what are we talking about when we say vibration? Well, it's just what it sounds like, a really fast back and forth motion. Think about it. You pluck a rubber band, you can see it wiggle. Or when you speak, you can literally feel the hum in your throat from your vocal cords vibrating. That motion pushes on the air particles around it, creating a disturbance, a ripple of energy that spreads outwards. And that energy, that is sound. The core principle couldn't be simpler. No vibration, no sound, period. Okay, so we've got this energy, but how does it get from, say, a guitar string all the way across the room to your ears? It doesn't just, teleport. It needs something to travel through. And in physics, we call that a medium. This can be a solid, a liquid, or a gas, like the air all around us. Now, this is a really important point, a common misconception, actually. When sound travels through the air, the actual air particles aren't flying across the room and into your ear. Instead, each particle just bumps into its neighbor, passes the energy along, and then pretty much goes right back to where it started. It's the disturbance, that wave of energy that's actually traveling, not the air itself. Honestly, the slinky analogy is the perfect way to picture this. If you give one end of a slinky a sharp push, you see this area where the coils get all bunched up, right? That's what we call a compression. And you can see that compression travel all the way down the slinky. Right behind it, the coils spread out again. That's a rarefaction. The key thing to see is that the individual metal coils just move back and forth a tiny bit. It's that wave of compression and rarefaction that does the traveling. And that is a perfect picture of how sound moves. So to get a little more technical, we can define a sound wave as exactly that, a series of these high-pressure spots, the compressions, and low-pressure spots, the rarefactions, moving through a medium. Because the particles are wiggling back and forth in the same direction that the wave is traveling, we call it a longitudinal wave. And since it absolutely needs a medium to travel, we call it a mechanical wave. Right, so if all sound is just this wave of bunched up and spread out particles, then how come a violin sounds so different from a big bass drum? To answer that, we've got to look at the specific characteristics, the DNA, of the wave itself. The easiest way to think about this is to draw a picture of the wave. You get this familiar wavy line. The very top of the wave, the peak, that represents the point of maximum compression. That's where the air particles are most squished together. And the bottom of the wave, the valley, that represents maximum rarefaction. That's where the particles are the most spread out. Okay, so one of the key properties of this wave is its wavelength. All it is the physical distance from one peak to the very next peak, or from one valley to the next valley. It's basically the length of one complete wave cycle. All right, next up we have amplitude. On our graph, the amplitude is just the height of the wave, from the center line up to the top of a peak. And amplitude, well, that's all about energy. The more energy you put into that first vibration, like hitting a drum really hard, the bigger the disturbance and the higher the amplitude of the wave. Okay, so we've got these physics concepts, right? Wavelength, frequency, amplitude, but what does that actually mean for us, for what we hear? How does our brain take all that science and turn it into the actual experience of pitch and loudness? Well, it's actually a surprisingly direct translation. The frequency of the wave, which is just how many of those wave peaks pass by a certain point every second, that's what our brain interprets as pitch. So more waves per second means a higher frequency, and we hear a higher pitch sound. And the amplitude, the height of the wave, its energy, our brain interprets that as loudness. A wave with a bigger amplitude sounds louder to us. Simple as that.
Let's put it into real-world terms. A thin guitar string, it vibrates super fast. That creates a high-frequency wave and we hear a high note. A big, deep car horn, it vibrates much more slowly. That's a low-frequency wave and we hear that deep, low-pitched sound. Same for loudness. If I just tap my table lightly, that's a small vibration, a small amplitude wave, and you hear a soft sound. But if I slam my hand down, big vibration, huge amplitude, and a much louder sound. See? It's all connected. So sound waves are traveling out from their source, but they don't just go on forever in a straight line. Eventually, they're going to run into something, right? A wall, a mountain, a building. And when they do, they bounce off of it. And that bouncing back is what we call reflection.
And this reflection is what's behind the echo. But here's the thing. An echo isn't just any reflected sound. To be a true echo, that reflected sound has to get back to your ears with enough of a delay that your brain hears it as a totally separate event from the sound you made in the first place. And it all comes down to timing. It's about how our brains work. You see, your brain actually holds on to the sensation of a sound for about 1/10 of a second. So for you to hear that reflection as a distinct, separate echo, it has to take at least that long, that 0.1 seconds, to travel to the surface, bounce off, and get all the way back to your ear. And this is where we can do some really cool simple math. We know sound travels through air at about 344 meters per second. We also know our brain needs that 0.1 second gap. Well, in that 1/10 of a second, sound can travel about 34 meters. That's the total round-trip distance, there and back. Which means the wall or cliff or whatever it is has to be at least half that distance away from you, or about 17.2 meters. That's the minimum distance to hear a clear echo. Any closer, and the sound gets back too fast, and your brain just mushes it all together. Okay, but what happens when you're in, say, a big empty gymnasium? You shout, and you don't just hear one clean echo. Instead, you get this big wash of sound that seems to hang in the air. That is called reverberation. What's happening is your voice is bouncing off everything, the walls, the floor, the ceiling, creating thousands of reflections that all blend together. And that's actually why concert halls have all those soft curtains and carpets to absorb the sound and cut down on unwanted reverberation. So everything we've talked about so far has been about sound within the range of human hearing. But here's a mind-blowing thought. The sounds that we can actually hear, it's just a tiny, tiny slice of the full spectrum of sound that's happening all around us all the time. As humans, we can typically hear frequencies from about 20 hertz on the low end up to 20,000 hertz on the high end. But there is a whole universe of sound happening outside of that little window. Frequencies below 20 hertz are called infrasound. These are super deep rumbles that elephants use to talk to each other across miles of land. And then above 20,000 hertz, you've got ultrasound. These are the super high-pitched sounds that bats use for echolocation, basically seeing the world with sound. And what's amazing is that even though we can't hear ultrasound, we figured out how to use it in some incredible ways. We use its high-frequency vibrations to clean super delicate parts. We can use it to detect tiny, invisible flaws in metal structures. And of course, in medicine, it's a total game changer. We use it for things like medical scans to see inside the body, and we can even focus those sound waves to break up kidney stones without ever making a single cut. So when you think about it, we've gone from a simple wiggle creating a wave of pressure all the way to these incredible technologies using sound we can't even hear. It's just so clear that sound is shaping our world in these profound ways, and most of it is completely imperceptible to us. It really makes you stop and think, doesn't it? What other invisible forces are out there shaping our reality every single day?